the limit at infinity. This time, the limit at, that means when x approaches infinity or x approaches negative infinity, what y approaches to, okay? So that's kind of the other way around of the 2.4. And then we look at the end behavior. Same graph of what we used in 2.4. As x approaches positive infinity, think about the real number line. You have the x and y axis. X and y axis, okay? So look at the x direction. When you look at the limit as x approaches infinity, that means all the way to the right side, all the way to the right side of the xy plane. What happens to the graph? So look at the graph. The graph go toward to that direction. And in this case, the graph, the right tail of the graph approaching the line y equals m. Therefore, that's the y value. So y approaches m as x approaches infinity. So that is the end behavior, the right end behavior of the graph. And then similar way, in the negative infinity side, so that means go all the way to the left side of the graph, where the graph approaches to, approaching to the value L. So that's the y value, y approaching L as x approaches negative infinity, I mean, all the way to the left side, the left end behavior of the graph approaching the value L. And approaching that value, that means in the long term, the graph will go toward to these two lines. So the lines that the graph approaching to for each end is called the horizontal asymptote. Horizontal asymptote. For the another way to explain, as x approaches infinity, that means when x gets very large, x gets very large, or the other way we call it without bound, okay, in a negative way or a positive way. When x gets very large, what happens to the y value? Okay, what happens to the y value? Okay, and some tools that we're gonna use on the second box here. Limit of the reciprocal 1 over x to the n. See, the numerator is fixed to be 1. Denominator depends on the x value. As x approaches the large quantity, the big number, when you raise to the power n, it's going to get larger and larger, right? It's opposite way of the one that we look at in 2.4. 2.4, when x approaching to, for example, 0, the denominator gets so small, smaller and smaller. But this case, the denominator gets larger and larger. So when you divide any real number by the large quantity, the quotient will become small and it will approach 0. And similar way to the negative infinity, like negative 1,000, negative million, whatever the number that you can name off as a very, very large quantity, you raise to the power 2, power 10, the quantity gets even larger. So 1 divided by very large quantity approaches 0 as well for the negative infinity side. Okay, so in the box here is the tool that we're gonna use most of the time in section 2.5. Oh, by the way, on the left box here, we have like 4 different cases. This case we call the infinite limit at infinity. You see 2 separate things in the phrase here. At infinity, I mean, when x approaches positive infinity or negative infinity, infinite limit is the y value, where y approaches either positive infinity or negative infinity. So you have 4 combinations. See, y positive infinity, x positive infinity, y negative infinity, x positive infinity, and so forth. For the, let me pick one of them here. For the last case, x approaches negative infinity, that means x go to the left side and y coming toward to the negative infinity. So the graph would go something like this. As long as you move over to the left more and more, the graph going down more and more, not approaching to anything. Okay, and for this case, as x approaches positive infinity, x or the y approaches negative infinity, the tail of the graph would coming downhill like that. Okay, so 4 different cases as a combination of the infinity of the x and y. Okay, and then for this example, it's pretty much like to use the two, like the in the box, the right box from one of the slides earlier. I mean the previous slide that we just went over. From the limit of 1 over x to the power n equals 0 as x approaches positive infinity, which gives the same result as 1 over x to the n as x approaches negative infinity. Okay, that means the denominator gets larger and larger and larger, either positive quantity or negative quantity. Okay, for number 1, you have 2 terms, and look at the x approaches infinity, negative infinity, negative infinity. We are talking about the limit at infinity. Okay, so we find the limit. Well, limit of the sum is the sum of the 2 limits. I'm just break it down for this problem, and then we can do in a quick way for the rest of them. Okay, limit 5 over x squared as x approaches infinity. And this one by the limit law. Okay, by the limit law, we can take 5 as the coefficient. So the constant multiple, limit of 1 over x to the second as x approaches infinity. And look at the first one, limit of 3 as x approaches infinity. No x involved. So the first term will always approach 3. Okay, and the second one, coefficient 5, and the limit 1 over x squared, but the denominator get larger and larger. We use this property to help out. So that means we're going to have 5 times 0. And the result of the first limit going to be just 3. Okay, that's the full version of work for number 1. It's a little bit too much, right? So we can do it real quick by noticing the term. All right, we have 1, 2, 3, 3 terms for number 2. And limit as x approaches negative infinity. That means when x gets very large in the negative side, what happens to each term? What happened to the 5? It's approaching 5. What happens to 1 over x when x gets when x approaches negative infinity? See the property that we're going to use? This term approaching 0. And the same as the last term approaching 0. Therefore, the limit of number 2 is just 5. Okay, because the numerator is the real number, but x changing all the time for the denominator, and x changing in the large quantity way. Okay, all right, number 3. What do you think? What can we do? Number 1 and number 2, they didn't look that bad, right? Number 3, how would we work on number 3 using similar concept or similar way to what we did in number 1 and number 2? And the limit at infinity. As x approaches infinity. So we're going to look at in the long run, what happens to each term? Eventually, what happens to that term? What happens to y value? Okay, as x approaches infinity or negative infinity. We use the same strategy as 1 and 2. 1 and 2 are very obvious that you have separate terms. Now we're going to separate the expression of number 3 to be the limit of x squared over x squared plus 2x over x squared. Try to break them up to see each term individually. Okay, so we get the limit of x squared over x squared is 1. 2x over x squared would be 2 over x. And the last term is 5 over x squared as x approaches infinity. So it looks similar to number 2. You have like 3 different terms, and you can look at one at a time. Are you okay? You guys have questions after before we go to the next part of the problem? So far, so good? Yeah? Okay. So could you tell me like for the limit of the 1, what do we get as x approaches infinity? You can type in the chat if you like. For the limit of 1 as x approaches infinity, what should we get? We get 1, yes. And how about the limit of 2 over x as x approaches infinity? As x approaches infinity, what happens to the 2 over x?
Should it be 0?
Yes, it's going to be 0. And how about 5 over x squared?
The same thing.
Yes, it's going to be the same. Oh, where did it go? I lost my, sorry. So the 2 over x approaching 0 because 2 divided by larger and larger and larger quantity approaching 0. Similar to 5 over x squared approaching 0 as well. So the result of this limit going to be 1. Okay. If you recall in pre-calc, you find the horizontal asymptote by looking at the coefficient of the leading power. If they are the same, you divide the coefficient with the coefficient. Do you recall that property? Kind of, right? It will come back. That's the byproduct of this section too. We're gonna get the horizontal asymptote. So to wrap up, when you take the limit as x approaches either positive or negative infinity, gonna tell you about the end behavior of the graph, either the right end or the left end, because the right end as x approaches infinity, the left end x approaches negative infinity. Okay, that's the concept or something that you can use to explain the limit at infinity. And for the transcendental functions, e to the x, e to the negative x, and natural log x, we can use the limit to explain the end behavior of the graph. Let's see, for the y equals e to the x, if you recall, the graph will be increasing graph like that. From the graph, what happens on the right end of the graph? Approaching infinity. Limit of the e to the x approaches infinity equals infinity. The left end, what happens? The y approaches 0, which is the horizontal asymptote. Okay. For y equals e to the negative x, negative power, so it's going to be different behavior, which is decreasing behavior. The right end approaching 0. And that will give you the horizontal asymptote. And the left end, what happened? The graph keeps going up more and more and more. The y approaches infinity. And the last one, oops, anyway. So the natural log of x, y equals natural log x. Natural log x, x is defined, log x is defined when x is greater than 0. So no graph on the left side of the xy plane. So we know this is your vertical asymptote of the log graph. And again, log and exponential, they are inverse of each other. You can flip-flop, you can flip 10x to y to x. Horizontal asymptote become vertical asymptote and so forth. With the behavior of the natural log x, as x approaches infinity, what happened to the graph? Approaching positive infinity. Okay, how about the left end? You cannot go all the way to the negative infinity because nothing defined here. Nothing defined on the left side. So the left end is going to be just toward to the bound here. As x approaches 0, positive, see it has to be remain on the positive side. The behavior of the graph approaching negative infinity.